In this video, we're going to be discussing the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus from Calc 1 came in two parts. The first part explained that the derivative and the integral are actually inverse operations of each other. Or another way of stating that is that the integral is actually asking us to find the antiderivative. So if we're asked to find the integral of the derivative, we're really asked to find the antiderivative of the derivative, and they actually are going to cancel each other out. The second part of the Fundamental Theorem of Calculus stated that when we're evaluating definite integrals, once we do that cancellation process, we only need the endpoints of our interval to calculate what the value of that definite integral is going to be. So to kind of summarize, the Fundamental Theorem of Calculus that we've seen so far states that to calculate the integral of the derivative of f, all we need to do is evaluate f at the boundary points of that interval. Our fundamental theorem of calculus here in Calc 3, talking about line integrals, is essentially the same exact idea. Again, we're given a curve C through space that is going to be defined by a vector function r of t on some finite interval from a less than or equal to t less than or equal to b. Now, if f is differentiable, we're going to be able to find that gradient of f. And again, if that gradient of f is continuous on C, then if I'm taking the integral of the gradient, I'm really taking the integral of the derivative of f. And all we're really going to need is to actually evaluate f at the endpoints of my interval, which are going to be the endpoints of my curve in space. Now, it's a vector function, which means that, again, when we plug in values for t, we're going to be getting vectors that point to particular points in space as our endpoints here. And so, again, our fundamental theorem of calculus, if we're taking the integral of a derivative, all I need is going to be the boundary points of that interval. The proof of this is in your book, and it's actually fairly easy to follow. It just has to do with how we define the gradient and the derivative dr, and we do a dot product, and that actually works out pretty nicely. And I highly recommend that you try to at least look through it once. But I want to focus mostly in this lecture on doing some examples. But before we get to the examples, I just want to review a few concepts that we've talked about before. First of all, we state that a vector field f is conservative if there exists a function f such that the gradient of f equals that vector field, equals f hat. All right, so a vector field is conservative if there exists a potential function, and we call f that potential function. Essentially, f is conservative if it's equal to a gradient. Also, I wanted to remind you that in our previous lecture, in that previous video, we actually showed that the path we evaluate our line integrals is going to matter. If I take two different paths, I'm going to get two different results. But what the fundamental theorem of calculus states is that if we take that line integral over a conservative vector field, right? If we take that over a conservative vector field, then we only need to concern ourselves about the endpoints. We're not going to have to worry about doing our parameterizations. All I need to do is find a potential function for our conservative field, and then evaluate that potential function at its endpoints. This is called being independent of path. So essentially, if the path doesn't matter, if we only need the endpoints, right? If we only need the endpoints, then the path doesn't matter, and our line integral is going to be independent of path. So let's get to our first example. So we're given a vector field f, and we're given a curve c that's defined by just a curve in space, in this case y equals 1 over x, and we have our endpoints. And so again, we want to evaluate this line integral. Now normally we would have to try to parameterize our curve c, and then from that parameterization, parameterize our vector field f. But here's the genius part of this. Here's the beauty of this. If I can show that my vector field f is conservative, I'm going to be able to find a potential function for that and just evaluate at the endpoints. Well, so the first thing we're going to want to do in all these problems is just check to see if my vector field is conservative. So the way we check if a vector field is conservative is that we take partial derivatives. So remember, we say P and Q are our component functions of that vector field, P being the component of X, Q being the component of Y. And essentially what we're trying to do is apply Clairaut's theorem here and verify that, well, if the partial of P with respect to Y is the same as the partial of Q with respect to X, essentially we're stating that it must be conservative if those two things are equal, because we're saying F partial XY, which is P partial Y, is the same thing as F partial YX, which would be Q partial X. So we're just taking two quick partial derivatives, and these are polynomials, so shouldn't be too bad. So P partial Y, take that derivative with respect to Y. Well, the derivative of 3 is nothing, goes away. And when I take the derivative of 2xy squared, well, the 2x, that's a constant. I can factor that out. And then the derivative of y squared is 2y. So 2x times 2y is 4xy. Now we take the partial derivative of q with respect to x. So I take that partial derivative. Well, the derivative of x squared is going to be 2x. So 2 times 2x times y is 4xy. They match. They're the same. Since they are the same, we know that that vector field is going to be conservative, and therefore a potential function must exist. So now our goal is to find that potential function. So now we're going to find the potential function by taking integrals. And we're going to integrate each of our component functions P and Q individually and try to match them up at the end. Now, I got to integrate P with respect to X. And again, just go slow at first. Be careful. Make sure you're trying to understand what you're doing, right? When I did the first step, my derivative of P was with respect to Y, but now I'm integrating with respect to X. All right? So again, just take your time and be careful. So when I integrate 3 plus 2xy squared with respect to x, well, the integral of 3 is 3x, and the integral of 2x is x squared. We treat that y squared as a constant. And so it looks like that integral is going to be 3x plus x squared y squared plus c. But again, remember that plus c is really going to be a function of my opposite variable here. So it's really going to be a function of y. And again, we typically write that as g of y. Now we need to integrate q. We're going to integrate q with respect to y. So the antiderivative of 2x squared y with respect to y, well, the antiderivative of y is 1/2 y squared. The constant part would have been the 2x squared, but 2x squared times 1/2 y squared, the 2 and the 1/2 basically cancel. So I get x squared y squared, and then my plus c. And of course, that plus c is actually a function of x in this case. And again, typically we'll write this as h of x. Now, my strategy is just try to match these up, build my potential functions from these results. You could, of course, and it is in your textbooks, you can go through and there's a systematic algorithmic approach where you can now, that you took an integral, you can take a derivative. But again, I'm just going to try to match these up. So first things first, let's match up. Well, what's the same between these two functions? And hopefully we can clearly see that my potential function is going to have an x squared y squared. That's the only thing that these two functions have in common. And let's see if we can build the rest of it. So I had that 3x from my first integral. So that 3x, well, that's going to match up with having just a function of x from my second integral. So h of x, my function of x, is just 3x. So we're absolutely going to include that. And then what about that gy? Well, is there any other function of y? No, there's nothing else we need. That's not even going to matter in this case. So my potential function is just going to be x squared y squared plus 3x. So now that I found my potential function, the last step really is just to now evaluate that at my endpoints. I know that I can now use that fundamental theorem of calculus here, all right, and actually just evaluate f, my potential function, at the two endpoints given in the beginning of the problem. So the two endpoints were 1, 1 and 4, 1/4. So, well, yeah, obviously do the upper limit of integration first. So evaluate at for 1/4 in my function for f, that x squared y squared plus 3x. You're plugging that into that function. Then you're going to plug in the ordered pair 1, 1 into that same potential function, find the difference, and get your result. I'm not going to do the arithmetic for you. You should be doing this arithmetic on your own. So pause the video, do the arithmetic, plug those values in, and hopefully you got the same thing as me, which is 9. And again, if you didn't get the same thing, double check. I tried to plug it in, and hopefully you got the same answer as me. For our second example, we're asked to find the work done from moving a particle from the ordered pair 0, 1 to the ordered pair 2, 2 through a vector field given as x cubed in the I hat direction and y cubed in the j hat direction. All right, so just to refresh our memories, by definition, work is equal to that line integral of integrating over the curve C of f dot dr. Well, I mean, user context clues, people. This is a section on the Fundamental Theorem of Calculus, and they didn't even give you a curve C to work with, which means that this is going to be independent of path. I'm only going to need the endpoints here because they didn't even give me the path. Plus, again, it's the section on the fundamental theorem. So we're going to be using that fundamental theorem, which means that for that vector field f, I am going to absolutely be able to find a potential function. So that's the first step, is to find that potential function. And again, I mean, check to see that there is a potential function, but that should be pretty easy. You'll find that py, or p partial y, and qx, q partial x, those are both going to be equal to 0. And you work backwards. And after you show that it's conservative, you find that potential function. All right, 1/4 x to the 4th plus 1/4 y to the 4th. And again, hopefully you get that without me having to kind of go through it. And then if we get there, then all we got to do is evaluate the endpoints. And again, what's going on here is that by finding that potential function, right, my formula for work, which was the line integral of f dot dr, we know now that that vector field f is really just the gradient of f, which means now that I know that I'm integrating the gradient, I'm integrating the derivative. All that's going to matter is my endpoints. All that matters is my endpoints, and it doesn't matter what the path is that I chose. And so, again, just plug in the endpoints. Plug in the ordered pair 2, 2, plug in the ordered pair 0, 1, and hopefully you get the same answer as me, 31/4 at the end. And again, go through, do that arithmetic on your own. That is basically the fundamental theorem of calculus. That's the core part of the practical knowledge that you need to take away from this section. But we need to take a little bit of time and talk about some specific definitions. So our first definition is we say a path is closed. So again, a path C or a curve C is closed if its initial and its terminal points are going to be the same. That essentially, if I evaluate my vector function at B and I evaluate my vector function at A, I'm going to get the exact same vector on my interval from A to B. And again, that should be true for any point that I picked on this closed curve. And so again, the simplest closed curve is just a circle or an ellipse, but it can look like anything as long as it's closed. The next definition is simple. We say a curve is simple if it never crosses itself. So that curve on the left is simple because it travels through space and never loops back on itself. That second one is not simple because, as you can see with the red arrow, it crosses back on itself at a point. So that means it is not simple. The next definition is going to be open. Now, a region. So we're not talking about a curve now. We're talking about a region in space. And again, this is kind of a preview. Our next section is going to go back to double integrals and stuff from chapter 15. And we're going to be talking about regions in space, typically represented by D. But we say that a region is open if it does not contain any of its boundary points. And this is very, very similar to how we define open and closed intervals back when we were just talking about, intervals of, say, x, right? If it's strict inequalities, that's open. We're not including those endpoints. If we do include the endpoints, then it is closed. So open just means we don't contain our boundary points of a region D, and it's just basically extending our same definition from one-dimensional intervals to two-dimensional regions, and similar to closed. So the thing is, you could also have a third type of region, one that's some of the outside is open, some of it's closed. Don't worry about that too much. Just worry about what does open mean and what does closed mean for right now. And again, when we talk about a closed region, there's going to be the interior points on the inside of my region, and then obviously the points that define my boundary. All right, those boundary points as well. The next definition is going to be about what it means to be connected. So what connected means is that if I draw 2 points in my region and anywhere, and it's maybe even a good idea to kind of practice here, draw 2 points in that region anywhere you want. Can you connect those 2 points with any curve whatsoever that still lies inside of that region D? All right. And if there's no holes in the region, then we can say it's also simply connected. So if you look at the pictures, that first one on the left, it's simply connected. So that region is simply connected. It's just one region. It's about as basic as a region gets. The one in the middle is a connected region. And again, this is where I kind of encourage you. Take that picture with a hole in it, right? Take that region with a hole in it, put 2 points anywhere in that region, and then try to connect the dots inside the region. You're going to be able to do it, even with the hole. You just kind of need to go around the hole. So that region is connected because you can connect 2 points together. It's not simple, though, because it has a hole. That last region on the right, furthest one to the right, it is not simple, and it is not connected. So it's not connected because if I had a point in the top region and a point in the bottom region, there is no way to connect those 2 points without leaving the region itself. All right. Now, it's time for some important facts and theorems. So I'm going to go through mostly just the basics and kind of the important intuition part here. Your book goes through a little bit more of the formal mathematics, and it uses those definitions we just talked about. But again, I want to focus mostly on just the core concepts here. So the first thing I want to talk about is if we have a closed path, all right, which we just talked about before, right? Closed means it's just basically like a circle almost, and it has positive orientation. Positive orientation means that we're only traversing the path exactly once, so that the initial point and the terminal point are going to be the same, and it must be in a counterclockwise direction. Now, we're going to stick with just saying that it's in the counterclockwise direction for now. However, when we start doing things in 3 dimensions, which is going to be coming up, fairly soon, what does it mean to be counterclockwise in 3 dimensions? Well, essentially what we're going to mean by positive orientation is that imagine you're walking around the path yourself. As long as the inside of the region is to your left, that's positive orientation. All right. Now, that's going to be very important for, again, how we set up our integrals, right? Obviously, if we do upper bounds and lower bounds, these things matter. The nice part is we're going to have notation that makes this much more compact. So if I have a line integral over a closed path C that has positive orientation, essentially we can take care of all that notation that it's a closed path and it's got positive orientation, and it also means that it's piecewise smooth. So positive orientation, piecewise smooth, aka POPs. If that line integral, again, it's closed path, positive orientation, piecewise smooth, we put a little circle around our actual integral notation there, and basically that little notation says all of that stuff in English. All those words are written just so much nicer and more compact with putting a little circle around there. So again, that's just a notation thing that we're going to be using throughout the rest of the semester. Now, fact. This line integral is going to be independent of path by the fundamental theorem of calculus. So I'm just kind of going back and reviewing from when we first set up what the fundamental theorem of calculus was earlier in the video. Remember, independent of path means that I only need to evaluate the endpoints of my antiderivative to solve this integral. And in this case, the endpoints of my antiderivative, well, again, the gradient is the derivative, so the antiderivative of the derivative, we only really need to use our potential function f. So it's time for the first of our two important theorems. Theorem number 1, f is conservative if and only if the line integral is independent of path. So hopefully that makes some intuitive sense. The proofs are in your book, and they're really not that bad at all. Remember, though, when I use that phrase, if and only if, it means the theorem is going to work both ways. It means essentially that the converse is going to be true, meaning I can start with the hypothesis and get to the conclusion, or I can start with the conclusion and get to the hypothesis. They're going to be equivalently valid statements. So essentially, if I know that my vector field is conservative, I know that I can calculate that integral as it's independent of path. I also know that if I can evaluate my line integral independent of path, then my vector field that I started with must have been conservative. So again, that is a very powerful theorem that is very, very useful when we're trying to evaluate line integrals. Again, basically, that whole theorem just states that we can apply our fundamental theorem of calculus. The second theorem kind of makes use of our new notation as well. And this theorem states that the line integral is independent of path if and only if, for every closed path C, the integral is equal to 0. And again, if and only if, this can work backwards. So if my closed path on my line integral is 0, I know I can work backwards, and it must have been independent of path to begin with. So I want to do a proof just in one direction. Again, it's if and only if. It means that the theorem works in both directions. You can start with the hypothesis or the conclusion and reach the other one. But I just want to do the proof in just one direction for you. Now, when we do proofs of if and only if theorems, we do want to include arrows to denote which way we're working. So see, I have a little arrow pointing towards the right. That means I'm proving it in one direction. And if you were to go ahead and prove it in the other direction, you would draw a little arrow to the left for that part of the proof. So first of all, we're talking about a closed path. So just to reiterate what a closed path is, if I have a closed path on an interval from a to b, then that means my function evaluated at b and my function evaluated at a must be equal to each other. Or again, if I have a curve c given by a vector function r hat, then r hat of b must be equal to r hat of a. Now, the actual theorem part. So if my hypothesis is that the line integral is independent of path, well, we know that if it's independent of path, then that f dot dr can be replaced with gradient f dot dr. Well, we know from the fundamental theorem of calculus that the integral of the gradient only depends on the endpoints, which means I'm just evaluating my function f at the endpoints now, which would be r of b and r of a. You might already see what's going to happen here. Because we defined our path to be closed, which means r of b equals r of a, which means that when we actually do this line integral, we know it's a closed path. So again, I can use my new notation. Instead of just saying it's the line integral over c, I can say it's the line integral over a closed path c. We know that if it's independent of path, then the f hat, my vector field, is equal to my gradient of f, right? We make that substitution. And then by the fundamental theorem of calculus, I know that the integral of the gradient only depends on the endpoints. But in this case, my endpoints, r of b and r of a, are the same. So it's really the endpoint at b minus the endpoint at b. So f of r of b minus f of r of b is going to be 0. They're going to cancel each other out. And that's my theorem here. So that's all I wanted to cover with this video. Again, practice the homework, go through the notes. I have also included on Blackboard a separate file titled, well, What Happens When a Vector Field is Conservative, that links a lot of these theorems together. Take the time and please look through that file about, this claim that f is conservative means lots of different things. How do I check that it's conservative? Well, if it's conservative, there must be a potential function. If there's a potential function, I can apply the fundamental theorem. And they are all linked to each other. And it is very important to hopefully understand that so that we can apply that to everything that we do later on in this section. Thank you for listening.